So we're happy to have Chi-Ming Chang from Tsinghua University, who's spending his sabbatical at the Institute of Advanced Studies to tell us about the microstates of black holes in AdS. And I should say Chi-Ming will be here for this entire week, right? And if you have any questions about the talk or this topic, feel free to ask him. Chi-Ming can take it away.
Okay. Yeah, thank you for the introduction. And so I will tell you something about my four papers. So the first one is already 10 years old. It's one paper with my previous advisor Xi-Yin. And then there are three recently new papers, and with my collaborator Yixuan Lin and two students, Feng Li and Yi Xiaotao, and also a postdoc, Chang, and yeah, he's a postdoc at Oxford University. Okay. Okay. So let's start from something more basic. So I mean, black hole we all know are astronomical objects with gravity that's so strong that nothing, not even light, can escape from the region inside the event horizon. And in the quantum theory of black hole, there's a central dogma, and that's there as follows: that if we try to observe black hole from outside, and then the black hole can be described in terms of a quantum system of microstates. And these microstates evolve unitarily under time evolution. And one, maybe the most important characteristic of this quantum system is the number of microstates. And it's given by E to the equal to the entropy of these microstates. And the entropy is given by the area divided by 4 times G Newton. This is the horizon area. And so, of course, we would like to know more, not just the number of microstates. And so basically, our goal for this talk will be try to build black holes as CFT operators, and in this non-perturbative complete setting of AdS CFT. And then using this, we can study black holes or black hole microstates rigorously. And the particular model that we will work with is this AdS CFT correspondence. And on the AdS side, we have type 2b string on AdS 5 times S5. And on the CFT side, we have angles 4 super-Young mills. And so let me tell you a bit of what are the black holes in AdS 5 times S5 we have. So first, there are a series of supersymmetric black holes. And these black holes, first they are macroscopic, and they are solutions to some supergravity. And they preserve 2 out of the 32 supercharges. And in other words, they are 116 BPS black holes. And their entropy given by A over 4G Newton, and it's proportional to the n squared, and this n is the rank of the angles 4 super-Young mills. And these black holes has 2 angular momenta and 3 charges, and all these angular momenta and charges are of order n squared. And so they are actually the only black hole. I mean, you can try to see that if I can preserve more supersymmetry and still have microscopic black hole. But it turns out that there's no known microscopic black holes with 1.8. I mean, no 1.8 BPS microscopic black hole. That means if I try to preserve more supersymmetry, I do not have any black hole solution.
What about like multi-center configurations or black rings? Are they also not possible?
So here I discuss only AdS black holes.
I know, but the AdS are multi-center or like black ring type solutions.
I think there's no known such.
Are they ruled out, or they have just not ruled out?
I don't know whether you can rule them out or not,
but potentially they could be less supersymmetric, like as little BPS as this one. Like multi-center configurations.
If you have multi-center black hole, then you probably will have single center one that preserve more supersymmetry, or or the same amount, same number of solutions. Yeah. So.
And the black-green solution are just not studied.
I'm not sure it's possible to have black-green.
Yeah, it's one flat space, yes.
Yeah, they could have black-green and
but not
flat
in
space,
AdS.
but I'm not sure, but I think it's not possible to have black-green.
And there's no hints for their existence from the index.
Right, that's also true.
Because you know the work from Ying
Yes.
and
Yeah, and in this talk, I will also tell you something about near supersymmetric black holes, and in particular the near horizon excitation of these near supersymmetric black holes. And let me first give a summary of the results we have. So first, I will show you a classification of operators. So these are CFD operators, operators in equals 4 super mills, and that corresponds to gravitons or multi-gravitons. So these operators are the trivial, relatively trivial operators. And if our goal is to study black holes. And the next result is I will show you the first BPS non-graviton operators. So they are not in the previous classification. And in these operators in in SU2 equals 4 super Young mil. And a potential interpretation of these operators are they could due to the smallest quantum black hole. So, and next I would also tell you some result about the non-BPS operator, and I will show you. So we have computed one loop anomalous dimensions of millions of near-BPS operators, and potentially they due to the near horizon excitation that I talked about for the near-BPS black hole. And then
planar?
No, this is non-planar result.
Okay.
Finally, I will also tell you a conjecture and also evidence for the conjecture that all 1/8 BPS operators are actually graviton operators, and so there could not be any 1/8 BPS black hole. And this result is from the CFD side, and this shows some CFD evidence of why there is no 1/8 BPS black holes. Okay. So
you mean 1/8 BPS black holes that do not have a microscopic horizon?
We have I will show you a conjecture that is actually stronger. So the conjecture is that there cannot be any non-graviton operator, and so previously the evidence from Borg is that there's no 1/8 BPS black hole, and it could be that there are some non-graviton 1/8 BPS operator, but the number of them is not enough. But the conjecture is actually stronger. Okay. So this is outline of the talk. So I will first give some set up the background, and then I will tell you the result I just reviewed, and then give some closing remarks. So the setup is that we will consider n equals 4 super Young mills on S3 times R. So R is the time and S3 is the space of n equals 4 super Young mills. And then we will pick a supercharge Q out of the 16 supercharges and a conformal supercharge S out of the 16 conformal supercharges. And then with Q and S, and S is the BPZ conjugate of Q. And with Q and S, we can consider this anti-commutator and Q dagger. And using the superconformal algebra, we know that this anti-commutator is given by a linear combination of some charges. And the D here is the dilatation operator, and J1, J2 are some rotation angular momentum. And they generate rotation on R2 times R2, and this R2 times R2 contains the S3 of this S3. And we have 3 extra charges, and they are R charges, and they correspond to rotation for the S5 in the AdS5 times S5. And you basically embed the S5 into R2 times R2 times R2, and this Q1, Q2, Q3 are the separate rotation of these three R2s.
So you say that the S is the what kind of conjugate?
The BPC conjugate, basically the Hermitian conjugate if you consider radial condensation.
Mm-hmm. And under that conjugation, you have a positive inner product.
Yes. You can also think of, if I consider quantization on S3 times R, and then this dagger would just be the usual dagger if you consider S3 times.
So Q
and if you put the, I mean, this on the state operator correspondence also map to the case that you have R4 and some operator at the origin. And in this case, you do radial quantization, and the conjugation is the one that respect this radial quantization. And so we will focus on, for the first part of the talk, we will focus on BPS operator. And these are operators with this linear combination equals 0. So operator satisfies BPS bound. And so there's actually a very nice a setting that we can work with. That is, there is a one-to-one correspondence between the space of BPS operators and the cohomology of the supercharged Q. So the argument for this statement goes as follows. So it's actually a standard argument coming from Hodge theory, and we can try to make this analogy. So we have Q and Q dagger, and for our case, and in Hodge theory, there is an exterior derivative and a co-differential, that is d and delta. And in Hodge theory, we are dealing with differential forms, and there are some particular differential forms called harmonic forms. They are the forms that are annihilated by both d and delta. And from Hodge theory, we also know that there is a one-to-one correspondence between or isomorphism between the space of harmonic forms and also the space of different cohomology. And so for our case, the operators that are annihilated by both Q and Q dagger, they are the BPS operators or the 116 BPS operators. And then from this analogy, we know that there is an isomorphism between 116 BPS operators and the Q cohomology. So if we want to study 116 BPS operators, we can first try to study the Q cohomology classes. So now we would like to basically try to construct these Q cohomology classes. And one advantage that we have in 4 dimension is that there's no non-perturbative operators. And so the usual non-perturbative operators that we may have, for example, in 3D are the monopole operators, and in 5D they are incident operators. But in 4D, we do not have such non-perturbative operators. And that means that all the operators can be built from multi-traces of the fundamental fields. And now we can basically think of the fields and their derivatives as letters, and then every operators can be expressed as words, and they are the gauge invariant combination of these letters. And we will focus on BPS operators. So we will actually consider a subset of all the letters we have, and using these subset of letters are called BPS letters. And then the words constructed out of the BPS letters, we call them BPS words. So that may be a bit more explicit. So these are all the letters we have in n equals 4 Williams, and we have 6 scalars, and this phi ij. So these indices I and j, they are the SU4 fundamental indices, and this SU4 is isomorphic to SO6, the R symmetry of n equals 4 Williams. And we also have a fermion psi and psi bar, and they also carry one fundamental index and also another spinor index alpha, and the antichiral spinor index alpha dot. So this alpha and alpha dot can take value plus or minus. And of course, we also have gauge field and covariant derivative. And so because we want to construct a gauge invariant operator, so we will actually mainly use covariant derivatives, but not gauge field. So the BPS letters are the letters that are BPS. So that means satisfy the delta equals to 0 condition. And it's just a very simple exercise to pick up the set of letters that satisfy delta equals 0. And there are 3 bosons, 3 scalars, this phi I. And now the small I here can take value 1, 2, 3. And also fermion, also 3 fermions psi I, and 2 gauginos lambda alpha dot, and also a particular component of the self-dual field strength F. And so these are the fields we have, and they have delta equals 0. And there is also some particular components of a derivative, of a covariant derivative that has delta equals 0, and is this d alpha.
What is the last one?
Oh, write down the definition.
Related to A and A dot, right?
You mean this one?
Yeah,
Yeah, that's basically Pauli matrix, and it's
just the same.
the sigma mu alpha dot, and I pick alpha to be plus. Yeah. And this notation, sigma mu is basically and this image lies this mu basis.
So you are choosing a basis of independent fields, and then all the other are related. Or I mean, why are these the BPS letters? Why little f and not, I don't know, sigma mu?
Because you can compute their delta, and delta is this linear combination.
I see, because of the charge.
Yeah, because of the charge.
Okay, then the other are anti-BPS or
That's right.
no.
Somehow.
For example, if you have no R charge, it means the field strength need to be self-dual.
Okay, so
Yeah.
because you choose here delta equal to
Yeah.
plus charge instead of minus.
Right. So yeah, for each letter you can compute their dimension and also J1, J2, and Q1, Q2, Q3, and basically you want this linear combination equals 0, that particular letter. And so these are the letters we would like to use to construct the operator, and the operators will just be gauge invariant combination of these letters. Basically, we will consider traces of these letters. And before we do that, there is one very important simplification. That is, we can actually assemble these BPS letters into some formal combination. This one, and we call it BPS superfield. And to do this, we introduce 2 bosonic auxiliary variables, Z plus and Z minus, and 3 fermionic auxiliary variables, theta 1, theta 2, theta 3. And then this bosonic variable Z plus and Z minus, they are just put in there to keep track of the number of covariant derivatives that you can act on each letters. So we have this combination, Z alpha dot, D alpha dot, and then basically the power of Z counts how many number of covariant derivatives you can have. And but there's also one Z put in here, and for this index to contract with the index of this gaugino. And these theta auxiliary variables are basically just try to put all the letters together to form this superfield like things. And so you can see that if I mean, so these thetas are Grassmann variables, so they can have expansions up to the cubic power, and so each component in this expansion corresponds to some BPS letters.
So usually superfield transforms nicely under supersymmetry transformation. But what are the nice properties of this side?
So you can consider some other supercharge that commute with the particular supercharge I pick, and so these supercharge would act as translation in this theta, this Fermiani Grassmann variable space.
That's how you fix the 2 and the 1 and the 4, all those coefficients.
Oh,
Here you pick some particular linear combinations.
Yeah.
How are they determined?
First, by their transformation property, you can basically fix this form, but probably not these coefficients. And the coefficients are chosen such that you have a very simple Q action on the superfield. I will show you later.
Just a comment regarding the question. So this variables actually is the superspace variable for SU 1/3, which is precisely the commutant of Q inside PSU 2/4. The 3 is the theta, 1 is the
I think 1 and 2 slash. So there's a sub-algebra that commute with the supercharge I pick. That's actually PSU 1,2/3, and but the superspace here does not actually fully realize the symmetries of this residual superalgebra.
I thought this is the one for SU. This superspace.
Okay. Okay. Yeah, and with this, we can try to write down the operator that we call BPS words. And as I said, they are made of some gauge invariant combinations of these letters. For example, you can have these. I mean, this is a very simple example. You have some. I mean, recall that all these letters are unbounded matrices. So you can consider matrix product of them and then take trace, and then they will be gauge invariant, for example, like this. And it's very easy to translate this gauge invariant combination to the language in terms of superfield. So basically, we take some z or theta derivatives and to pick up some particular components. And so the advantage of this superspace is that, and superfield is that the Q that we were interested in act on psi in a very simple manner, and you just have a Q acting on psi give you psi squared. And so I mean, this is actually the classical Q action, and you may wonder that whether this classical Q action may receive some quantum correction, and actually in Lagrangian theory, so the action of Q on fundamental fields is undeformed perturbatively if you have some nice regularization that preserves supersymmetry. For example, the Siegel's DRED. And so if I have some SUSY preserving regulator, and then this relation would be undeformed by quantum correction. But this is actually not all the thing we need, because
this the red you mean the scheme, the one that Professor was saying. You said dimensional reduction scheme.
Yeah, some regularization scheme.
But what is the scheme?
I think it's the one that is compatible with supersymmetry, right? So out of the especially at loops, you have to pick up a dimensional some scheme for realizing. I say this one is a particular prescription, how to do that, and so on.
So there's different supersymmetry preserving scheme, the homomorphic scheme. So this is not the.
This is compatible with supersymmetry. I don't know.
There's also the Cyber's homomorphic scheme.
Yeah, they are. I mean, I just need one scheme that preserves supersymmetry, and then I'm fine that this will not be.
But you'll be calculating, but you're not going to calculate these two loops.
Yeah, I'm not going to.
So likely your answer is scheme independent.
Yes. Yes. But we actually need a bit more because I mean this rule only tell me how Q acting on psi, but I want Q acting on BPS words, for example, and BPS words are some composite that we made of psi. So for example, so we need to know how Q acting on a product of psi, and classically the Q action will obey the Leibniz rule. So Q acting on A times B equals Q acting on A times B and plus A times Q acting on B, and with some plus or minus sign depending on whether this A is bosonic or fermionic. And so the quantum effect may violate the Leibniz rule, and that's possible. However, there are some explicit computation that's done by this group of people at PI, and they found out that there's no correction to Q acting on BPS words up to some change of basis in equals 4 reals.
Perturbatively or not?
Only perturbatively, and their computation is just up to certain loop order.
Yes.
So actually, there is some non-renormalization conjecture that is saying that Q does not receive any perturbative or non-perturbative corrections. So in this talk, I will basically just assume this non-renormalization conjecture.
Sorry if I. So Q is the one that is your exterior, your boundary operator and your cohomology, right?
Yes.
So what means that if you are not acting on BPS in these cases in which you break the fact that would you break that Q is not nilpotent in that case, or what sense is can break the line? It doesn't satisfy this one, or it's just that acting on some operator and not BPS, it is not longer nilpotent. It's no longer.
So you can have some loop corrections to Q. So say the classical Q is called Q0, and you can have Q1 and Q2 and so on. And so say you have some perturbation theory, and you have a perturbatively corrected Q, and that's the sum of all these. And this perturbatively corrected one should be nilpotent, and that will give you some relation you should have for this Q0, Q1, and so on.
The naive one, the classical one is no longer nilpotent. You have to take
Okay.
But for the BPS sector, you can just continue to use the classical one.
The classical one is nilpotent.
BPS.
So this the fact that Q does not, the conjecture that Q does not have any correction is true only on BPS state?
Conjecture is only on the BPS state.
N equals to 4.
Yes, N equals 4.
Only for equals 4.
Yeah, only for N equals 4. And so in some examples, we know that Q can have correction. For example, the N equals 1 super Yang, N equals 1 pure super Yang. And that example, and they did like they found some corrections, and that would indeed change the Q chronology. And so that would be our working definition. And so now let me show you some of our results. So first, let me tell you a particular class of Q cohomology that can be exactly solved. And so first, we can notice that the Q action does not change the number of traces. So we can talk about the Q cohomology in the space of single trace words. And in this case, actually all the representatives of the Q cohomology has been solved. It is known. And so the way to see them is to consider D psi, this combination, and that you can think of this D as some formal exterior derivative acting on our superspace, the 2Z and the 3 theta superspace. So we have that combination. And then we would treat dZ as fermionic and d theta as bosonic. And now we can consider Q acting on this D psi. And very simple computation, you can see that Q acting on D psi is just the commutator of psi and D psi. And now we can very easily write down, for example, this combination. the trace of d psi to the n-t power, and it's quite easy to see that a Q acting on it is give you 0, because you can think of the Q action as a gauge transformation, and with the gauge parameter psi, this gauge transformation acting on this side. So Q acting on this guy will give you 0. And it turns out that all the single trace cohomology classes can be represented by these operators, and we will call them graviton operator. And by the reason that I will explain.
Sorry, so this has many components. So which degree should I look at? Every degree?
Every degree, okay. Yeah. So you can do expansion of this formula in terms of dc, d theta, and also in terms of this z and theta. And every component in the expansion will be a non-trivial, I mean, will give you some representative of cohomology class. Okay. And in larger limit, we can try to count how many cohomology we have, and then compare with the gravity side. And we see an exact match between the number of single trace cohomologies and also the number of single graviton states. So that motivates the name that we call them graviton operator. And we can now consider products of the graviton operators, for example, like this. And now let's consider finite n, and if you consider products in for finite n, then there could be some trace relations, but we basically can simply consider them modulo some potential trace relations, and they will correspond to multi-graviton states in a larger limit. And that's why we will actually call these cohomologies graviton cohomologies, and this cohomology contains both single graviton state and multi-graviton states. And but the important thing here is that we actually can define graviton cohomology at finite n. So our way to define graviton cohomology is basically to list the potential representatives for this cohomology, and there could be some relation among these representatives, but they cannot be. I mean, by our method, we actually, I mean, if we go from infinite n to finite n, there can be relations, but there won't be any new cohomology class. So we can basically define this cohomology even at finite n. So not just infinite n. And using this method, we can actually distinguish a graviton versus non-graviton at finite n order, and these non-gravitons potentially can contain black holes at finite n. Is this point clear?
But strictly speaking, the distinction between graviton and black holes is only meaningful in large n limit.
Right.
But so for finite n, it's more like just a definition that we know work in infinite n.
Yes. We kind of extend the notion of graviton versus non-graviton from infinite n to finite n. And we can see that in this cohomology language, there's a very natural extension.
But so people just say at finite n, we look at operators of large dimensions. We can tell apart multi-gravitons from black hole operators by looking at the degeneracies.
That's the next thing I will talk about. So the next thing is try to understand black holes.
I think there's a sense, yeah, just related to Shuhun's question, but there is a sense in which you can tell apart black hole operators and gravitons in a physically meaningful way at finite n.
Do we have a definition of the black hole operators?
Let's see. I have a meaning now.
Let's wait.
Okay. So first we can try to, I mean, basically count the number of graviton operators, and that just equals to the count of gravitons. And basically count of gravitons. I mean, we want to focus on the range of charges that are of order n squared. That's the black holes case. And so the number of them grows like e to the n to the 5/3, and but this is much smaller than e to the n squared, and e to the n squared is the number of black hole microstates we have. So this simple exercise basically tells us there must be non-graviton operators to account for the black hole entropy. And the second thing, it tells us that a typical black hole microstate corresponds to non-graviton operators. That is because e to the n squared is much larger than e to the n to the 5/3. So if I just randomly pick one black hole microstate, it shouldn't be. I mean, it should not correspond to it should not correspond to graviton cohomology. So we will actually roughly refer the non-graviton operators as the typical black hole operators. So any cohomology class that are not this graviton cohomology, we will call them in a loose sense a black hole cohomology.
So the graviton operators can be primaries or descendants? Or
Yes.
You don't distinguish between the two?
I don't distinguish.
But only special dependence can appear because of the delta equal to 0 condition.
So now the next question is to find the non-graviton cohomology, and I mean this is a straightforward problem, and I mean I've already told you the setup, and you can just try to play with it. They're taking traces of this size and derivatives, and then try to compute the cohomology classes, and then eliminate all the cohomology classes that are graviton cohomology. But it turns out that this problem is actually computationally very hard, even for small rank. And so basically, the thing we did last year is that we basically enumerate all the BPS words for the SU2 n equals 4 Swift mills up to some large classical dimension, E0. And then basically, by doing this, because we write the BPS words in this multi-trace form, there are a lot of trace relations involved. And the hard part computationally is to basically to enumerate all the trace relations. And after that, we basically get a million-dimensional Hilbert space. A million-dimensional Hilbert space of BPS words. And then we can try to compute how Q acting on this Hilbert space. So we know how Q act on a single letter. We also know, Q acting on the composites would just obey Leibniz rules, and then we would basically know how Q acting on every operators in this Hilbert space. And then using this, we explicitly constructed roughly 10 to the 5 cohomology classes.
So the claim is that from this million-dimensional classical BPS space, only like 10% is are the unequivalent cohomology classes?
Yeah, basically, yeah.
So
some of them are related by
yeah.
Q, and so they will form pairs, and this is not Q close.
So just asking if it's like a reduction by 10.
Yeah. After you take cohomologies, yes. The number of cohomologies reduced from the number of dimensions reduced from.
But the hard part of the calculation is the first part, not this. Is the hard part the eliminate trace relations or the second part?
Yeah.
The reason I'm asking is because there's a very similar calculation that condensed matter people do for I don't know how many years, exact diagonalization. You're going to study the spectrum, with some.
Hey, I will talk about studying the spectrum.
This is not
that
space.
I know. But there's a very similar numerical problem.
Yeah.
I was asking which part is hard here, because the first part doesn't have a direct.
There's no matrix yet, so it's not exact.
People get that.
I will talk about exact diagonalization in later parts. Okay. So basically, let me be more specific. For the SU2 case, we went up to this combination. I will call it level n, and that's 2 times the dimension plus a particular combination of spin. I changed my convention, so this J lab is J1 plus J2. Okay, J1 plus J2 over 2, and we use this number to basically grade our to give a grading of our Hilbert space, and then we went up to this level n equals 24, and then there are 10 to the 5, roughly 10 to the 5 cohomologies, and almost all these 10 to the 5 cohomology are graviton cohomologies, except this one. So it has dimension 19 over 2, and J left 5 over 2, and 0 J right, and also 3/2 for this QI. And you can see that this particular, I will call that non-graviton cohomology or black hole cohomology, it has a dimension actually much greater than n squared. So in this case, n is 2, so n squared is 4. But their separate angular momentum or charges are still roughly equal or smaller than n squared. And for SU3 and higher, we actually do not find any non-graviton cohomology. And for SU3, we go up to level equals 19, and for SU4, we go up to level equals 15.
Sorry, so I thought the expectation is that the graviton operator will dominate in terms of degeneracies over a non-graviton operator at some stage.
Yes.
And you say for the first almost like 10 to the 5, you
Yeah,
only have one single
right.
one.
It sounds like the opposite situation, and but that intuition is like non-graviton or black hole dominate, the black hole states dominate graviton states. That's a larger intuition.
But so for a large charge, I thought there's a corresponding statement that when I look at the efficiently large charge, I will see the similar dominance.
Yeah, I think it's also expected that if you go up
Exactly. So
large enough charge.
Yeah. So from this experiment, do you see how large charge you need to go in terms of?
You mean try to estimate how large charge? We don't have that estimation, but you can already see that it should be maybe much higher.
But don't people have some kind of evidence for, like Kim had the paper, like looking at an index? He has some argument for how large charge.
Graviton index.
Yeah. Compare the index contribution to the index from the multi-gravitons versus the full index.
I think so. They have some explicit computation for graviton index and the full index, and then the difference.
Yeah.
But that explicit computation are still at a relatively, a low level. It's roughly level 24 and something. Yeah. Like something close to 24.
Yeah.
But I think probably using that formula, you can try to have some estimation for a large
for larger chart, for larger little n, right? But it's not. No.
I think. Okay, I didn't do that, but I think I don't think they also did that. I think that maybe, I think that's interesting to explore. And you may wonder what the representative look like. So last year, Ying and I, we did some brute force construction of local homologies, and the representative we found was very complicated. But 2 weeks later, and the Korean group, they actually found a very concise and explicit representative for the same cohomology class, and it takes this form, and it's a triple trace. I mean, even though for SU2 the number of trace doesn't really mean much, but I mean it can be written as a triple trace form, and the first 2 traces are graviton operator, and the last trace is actually not Q close, and if it is Q close, then the entire thing will be a graviton operator. But and you can try to interpret the last one if you try to naively interpolate this operator to infinite n, then the last trace has the interpretation of a massive string state. And okay, so I mean this guy represents the cohomology, so it should be Q close, and you can actually check that Q acting is equals 0.
Just coming from the cyclic sum, that somehow the last term is not Q close from the cyclic sum.
Yeah, from the cyclic sum, and also the fact that you are at SU2, and there can be trace relations. And
can you generalize this representative to higher?
I will talk about some generalization, but you can generalize to higher charges, but so far not higher n.
Not higher.
Yeah, but for SU3, people do not know.
So it's very heuristic when you say this corresponds to the massive string.
Yes, so far. I mean, there are a bit more precise sense I can talk about them, but I delete that part in my talk. But if you are interested, I can do it later.
So how do we intuitively understand the third factor is not a graviton? Is it because it has more derivatives acting outside?
Right. So recall that the previous graviton form inside the trace, every psi has exactly one derivative acting on it. And in this case, there are two derivatives acting on psi.
Dumb question. So what if you just remove one of the graviton factor? Then
By hand.
By hand, yeah. Then that will no longer be Q close.
I think so.
I see.
Yes. Yeah. But this guy only represents the cohomology, and you may ask that, I mean, so we know that there's a one-to-one correspondence between cohomology classes and BPS operators, and that basically means that given a representative, there exists some Q exact operators, and if we add to this particular representative, we can make that operator BPS. And what Q exact operator we need to add, that actually depends on the loop order. And we actually carry out this computation at one loop. And at one loop order, we know that if we take this representative O, and we can add a series of Q exact operators. So this O3 to O17, they are basically given some Q acting on O prime 3 to O prime 17, and they are Q exact. And then the resulting operator is one loop BS. So this just show you the form of these O primes. And so that particular form of the representative there are some generalization. So by also this Korean group, so they found an infinite family of non-graviton operators. So the way they found it is basically they first construct an index called graviton index. That's basically is a partial trace over the multi-graviton operators. And they basically found out an efficient way to compute this index. And then you can try to compare the SU2 graviton index with the 4 index. And then the difference will give you the non-graviton operators. Basically, you can know the charges of non-graviton operators by looking at the difference between these two indices. And after knowing the charges, so the charges of non-graviton operators are actually quite important information for you if you try to construct some operator. And using that information, and they also restrict to the BMN sector. That means they consider a sector with only theta derivatives acting on this superfield side. And then they construct an infinite sequence of non-graviton cohomologies and at some higher and higher level. So the first one was the one that we've seen, and then there's the next one has at level 36 and also some higher level. And one open problem is that so far we do not know any non-graviton cohomology classes for n greater than 2.
So can one repeat the calculation for the graviton index when n is greater than 2?
Yes, so Ying and I actually had some result for SU3, and we found out that so Kin et al. Also has some published result for SU3, and And both of us found out that at level 24, there are some non-graviton cohomology.
But it's just numerically, it's very hard to get to little n equals to 24 for S3.
Yeah, that's a very quite hard computation.
So you stop at 19, and it's hard to get to 24.
Oh, for computing the index, it's feasible to go up to 24, but to construct the operator is actually hard.
I see.
Yeah, even though we know there are some non-graviton operator there, but we do not know how to. Our computational power is not enough to compute to really nail down that.
Do you think that for all n, the non-graviton operator shows up at 24?
It's unlikely, but it's not impossible.
Naively, you think it will shift higher.
Yes, right. Because
it should be, there you expect some kind of bound up by little n from below by capital N.
Oh, sorry, I think it's impossible.
Okay.
For
Just for inclusive 3, it happens to be still 10.
Yeah, because if you consider large n and then a dimension lower, a dimension charge is lower than n or something, everything should be
That's right. Like capital N.
Okay, so next let me tell you something about non-BPS operators.
But there could be that this black hole operator you find is non-graviton, but there could be something in the middle.
Yes, that's possible.
And that could survive even for large n, capital N.
But their dimensions should at least deal with n, I think.
You think? If it's not related to black hole, why the dimension? You see what I mean? The working assumption here is that non-graviton is like a black hole operator.
Their dimension need to at least grow with n.
How do you argue for that? If you don't know actually.
Yeah, if the dimension does not grow with n, then let's take larger limit, and then you will have some finite dimension operator.
I see. You're saying by looking at the index.
Yeah. I mean, even without focus on index, in larger limit, we know it's a partition function, and there's no such all the finite dimension operators are just gravitons. So let me first discuss what's the expectation for the behavior of near-BPS black holes. So the near horizon geometry of a supersymmetric black hole contains an AdS2 factor, and so that basically tells us that the low energy excitations around this AdS2 on this AdS2 factor is captured by a n equals 2 JT gravity, and n equals 2 JT gravity is actually one loop exact, and people have solved the spectrum in the n equals 2 JT. And one very interesting character of this spectrum is that the spectrum has a gap above the BPS states. So the spectrum contains both BPS and non-BPS state, and the BPS states will be basically the ground state in this n equals 2 JT gravity. And then above this ground state, there's some gap, and then you have some non-BPS states. And this spectrum, this spectrum in n equals 2 JT also due to some random matrix theory under the AdS2 CFT1 correspondence. So now our question is that can we see this picture in gauge theory? So the particular thing we would like to see is this gap. This is like the characteristic we have for this near-BPS spectrum. And at weak coupling, the light excitation are captured by the classically BPS sector, and this is defined as follows. So we can, at weak coupling, we can work in perturbation theory, and then we can expand the dilatation operator in power series of G((-)) square, like this. And this D0 is the classical bare dimension of the operator. And then we can focus on a particular sector that satisfy this delta 0 equals 0, basically satisfy the BPS condition at the classical level. That means at G mills equals 0, we demand the operator satisfy the BPS condition. And these operators are basically the operators that you can construct it from taking the traces of these BPS letters. So they are basically the BPS words. So every BPS words, you have a corresponding classically BPS operator. The anomalous dimension in this classically BPS sector can be regarded as a Hamiltonian on of a supersymmetric quantum mechanics. That's just basically we take d minus d0, and that basically just gives us this charge combination, and that's the any combinator of Q and Q dagger, and we can call it a Hamiltonian. And we will focus on the one loop Hamiltonian, and in this case, because we already know how Q act, so to know the Hamiltonian, the only thing we need to know is Q dagger, and Q and Q dagger are related by the BPZ conjugate, this dagger. And at one loop order, we can actually take the dagger in the free gauge theory, and then that gives us a one loop Hamiltonian. But again, we have to define the problem is very simple, but to really diagonalize the one loop Hamiltonian, that's hard. Basically, we have, as I said, we have a million-dimensional Hilbert space, and we want to diagonalize the Hamiltonian that acts on this million-dimensional Hilbert space. And there's a sub-L. Okay, we want to organize the result using some symmetry algebra. That's a sub-algebra of superconformal algebra that commute with the dilatation. Sorry, this delta, this combination of dilatation operator and the momentum and charges. And so basically for the rank n equals 2, 3, 4, and so on, we have these many operators, and then we organize them as multiplets under this symmetry. And after that, we can look at what are the distinct values of anomalous dimension we have.
What is the infinity ST, infinity M?
Oh, that means we take n infinity. Then that basically means that we only focus on single trace.
A single
operator.
trace and multi-traces.
And MD means multi-trace. So we can consider Q acting on the space of all the multi-traces without any trace relation. That gives us this case. And it can also act on the space of only single trace. And then we can try to plot the spectrum we obtain. So we have these plots. So the x-axis is some combination. I mean, basically it's a one loop anomalous dimension, and with some proper normalization. And this y-axis is the density of operator. And one interesting feature we've seen is that it looks like there is a gap in the spectrum for SU2, but it looks like there's no gap for the SU infinity multi-trace case. And so the previous plot is for all the operators.
Is there a reasonable interpretation?
Yeah, basically the interpretation is from the box side. So people see a gap if you consider the n equals to JT gravity, and that's the sector at the near horizon region. And our result kind of nicely match with the Borg interpretation. So the Borg exploitation.
Sorry, but the bulk calculation is for infinite n?
Right, the bulk is for infinite n.
But you only see the gap for SU2.
Yeah. I will. I mean, there are some fine print. I will talk about that. Yeah. So I also have. So previous plot is for all operators, and we can also organize the operators in terms of the multiplets. And here I only plot the primaries. And again, we can see that there's a gap. It looks like there's a gap, and there is no gap for SU infinity case. And there are some fine print. So basically, the spectrum is discrete, so there's always a gap. And what do I mean by a gap in this case? A more precise definition of the gap is in some average sense, and the definition it can only be defined at larger limit. So basically, from the let me tell you a bit more. From the bulk theory, people predict that the gap is of order n squared, and so basically, if you consider this diagonalization problem, you can ask what's the typical gap you will have, and the dimension of the matrix is e to the s times e to the s roughly. So that's e to the n squared times e to the n squared dimensional matrix. And if you have this kind of matrix, and if the entries of the matrix are just roughly 1.
So sorry, I'm not an expert, so sorry if I make it good question, but so the HIT, when you see the gap in the spectrum, it is for infinite n, right?
Yeah.
So what it means that the gap you expect is 1 over n squared?
That's the scaling if you consider larger limit. And yeah, from a graph, from a bulk computation in a larger limit, people, and from the JD graph, people find that you should have 1 over n squared gap. Okay. And this is if you try to diagonalize some matrices and of rank n squared, and rank e to the n squared, and then the typical gap you will have of order e to the minus n squared. So the point is that the bulk you see a larger gap than the typical gap you will get from diagonalizing some matrices. And for here we consider SU2, and the spectrum is discrete. So there's always a gap because the spectrum is discrete. But our point is that the actual gap is actually much larger than the gap that we expect from diagonalizing some matrices.
Can you mean that you have a gap that is parametrically larger than the gap you will have just because you have finite n?
Yeah. And so here we also write down the actual gap we have. So you can try to compare that for the SU infinity case. Even though from this plot it seems that there's no gap, but there's an actual gap. But the SU2 case, the actual gap is kind of larger than the actual gap for the SU infinity case.
What is the value of coupling here?
We have some normalization of the coupling. So we show the anomalous dimension with this normalization, and lambda is the
okay. So E is only the anomalous dimension. Okay.
Yeah, E is the anomalous dimension. I think let me mention this. So there are some open problem. So first is that in our computation, this diagonalization problem, we didn't use all the symmetry, and we can also see that after we use the symmetry, the real multiplet with respect to this symmetry, the number of them is much smaller, and so and if we have a way to incorporate this symmetry in the computation, then that would make the computation much easier. And the next open question is there a similar gap for higher rank? And also, how does the gap depends on both M and the G mills? And there's also a question that because the near-BPS spectrum is not protected, but we still see some common feature from the bulk and from the CFT side, and whether there is some explanations for the why we see this common feature. Okay, I think I will skip the 1A BPS graph part and direct come to the conclusion. We've seen that the Q cohomology have provided more refined but still and while still protected information on BPS black holes, and we've seen the graviton operators and the black hole operators, and also we've seen some features of the non-BPS spectrum, while unprotected, may be shared by both the strong and weak couplings, and the feature I talked about is a gap above BPS states. And it may be possible that there are some more features, more refined features in the spectrum that we can extract, and that also shared from the shared by both weak and strong couplings. That's all I'd like to say.
Questions?
So, can you calling these operators graviton is because in the larger limit and using AdS CFT you can relate to something to the graviton, or
yes, yes. So these operators at larger limits, we see that they are due to gravitons.
The single state.
Yeah, but for single, for single trace cohomology, we see is that due to graviton, single graviton, and in a larger limit, and I mean the gravity size is weakly coupled, so the multi-graviton would just be given by products of single graviton.
here by graviton you mean graviton multiple or just
Yes,
some states
graviton multiples. So include the gravitino and some other fields in graviton multiple. And so by graviton actually means the 10-dimensional graviton. So if you view it as some supergravity in 5 dimension on this AdS5, so that also includes the KK modes from the computation of the AdS5.
For example, all the BPS operator that people are studying, like which the correlation functions amplitude EVS, there are multi-graviton operators, mostly single trace graviton operators in the language.
But for finite n, do you think there's a more physical way to define a graviton operator? Maybe this class of operators have some special quantum numbers or something. I understand the reasoning you provide. You say take large n, they becomes the graviton in the bulk. That's great. There is a natural definition extended to finite n. I'm just wondering, if I never go to infinite n, I just look at those class of operators. Is there something special about them? That's for 1/8.
All the graviton operators are in the Kerr algebra.
Oh, no. So for 1/8, then I mean if you preserve more supersymmetries, and then all the graviton operators are
so not all the so there are additional ones.
Yeah, they are.
So the intuition comes from large limit. So it's
Basically,
the single version of them is the one that in the large infinite n gives the graviton multiple.
Right. Yeah, and even these cohomology.
But there is another version of the Kerr algebra, right? The one, the semi.
Semi-chiral.
Yeah, it's a semi-chiral, right?
Oh, yes.
That captures the entire 160 BPS.
Right, that captures all the 160.
So in that case, is there a way to characterize the graviton operators in that framework?
Compared
to
in that framework, No, people.
Finite.
Finite.
Oh. So so basically you first consider the single trace cohomology.
Yeah.
And you can define like finite n.
Yeah.
And then you can consider products of the single trace cohomology.
But it's the same thing you were.
Yeah, the same thing I discussed. And that's the only definition I know.
So there is, even in the semi-current ring, there isn't a sense in which, like, the multi-graviton generates some kind of algebra, and everything else will be representations. And if you look at the vacuum module, you just look at the multi-graviton. I cannot say something like that, even in the semi-current ring. Because if you can do that, then this will be.
So when you talk about modules, you may first want to define the products of these operators.
Yeah.
And
They close.
okay, in the Cairo algebra case,
Yeah.
you can take the OPE and
Yeah.
then take some cohomology and
Yeah.
then get
That's
some
right.
productive
Yes.
OPE.
Yes.
But in the semi-Cairo
Yeah.
ring case, I'm not so sure.
It's not.
At least in the literature, I do not see that part of the discussion.
So the graviton operators may not close.
Okay, first you need to define this. So you have some algebra. You need to define. I mean, if you want to talk about algebra, you need to define the product. The product, yeah.
Yes.
And so there are some discussion of. So I hear from Jixiang Wu.
Yeah.
And he told me. Yeah, there are some algebraic structure called higher Virasora or higher algebra structure, but yeah, I'm not that familiar with this structure. So that basically, so the Cairo algebra is defined on a single complex plane, and they try to consider C times C. You have C2.
Yes.
And then that's what they call the higher algebra. And you can try to define some products for this higher algebra.
Okay, let's thank Chi-Ming again.